Then we have this concept called mean free path. Gases are going to travel until they run into something. The mean free path is the average distance that a molecule travels before it runs into something. As you can kind of deduce, the mean free path is going to decrease as the pressure increases. If you increase the pressure and make these gas particles closer together, they're going to run into each other more frequently. So the distance they can travel is going to be less. If nitrogen was the size of a golf ball, it would travel about 40 feet before it runs into something. And here we're looking at an illustration of a typical gas molecule path. Not sure what direction it's going. I think maybe it's coming from here. And it goes zoing, zoing, ding, dong. It's just bouncing around. I'm not sure what noise it makes. Now that I think about it, I don't think it's one of those. This reminds me of the Family Circus cartoons we used to see in the Sunday newspaper, where it would show Billy, going all over the place. But that's for the gas molecule. And we have these ideas of diffusion and effusion. And the words are spelled very similarly, and yet they are somewhat different processes. Diffusion is the process of a gas spreading out from high concentration to low concentration. And we find that heavier particles diffuse more slowly. Effusion is the process of a gas escaping through a small hole into a vacuum. So the way I remember this is effusion starts with an E and exit starts with an E. Effusion is gas molecules escaping, exiting a container. Both of these, the rates of diffusion and effusion, are related to that root mean square average velocity. And what this tells us is that for gases at the same temperature, the rate of gas movement is inversely proportional to the square root of its molar mass. Because that root mean square velocity equation was 3RT over the funky molar mass. Well, 3 and R are always the same. At the same temperature, then, a higher molar mass will mean a slower movement. So diffusion and effusion will be slower for heavier gases. Graham's law of effusion shows us about the ratio between two gases. So two different gases at the same temperature, the ratio of their rates of effusion is given by this equation, which you could derive fairly simply from that root mean square velocity equation. So the rate at which A effuses divided by the rate at which B effuses is equal to the square root of the ratio of their molar masses, B over A. So this is A over B, this one's B over A. So helium escapes from a balloon faster than air because of its small size. Rate of effusion is related to gases escaping from a balloon. So if you have a balloon that you filled up with air by blowing on it, and a balloon that's filled with helium, same exact kind of balloon in the same room right next to each other, and you wait, 2 days or something, the helium balloon will get small faster than the air balloon because the helium atoms are smaller and they effuse faster. They're going to get through the teeny tiny pores in the latex balloon faster than the regular air particles. Here's a little illustration of effusion. So here we have a vacuum. Well, it was a vacuum until a couple particles got in there. Here we've got a gas, and there's this little tiny hole, and the gas will escape, but the only way it can escape is if you've got one that gets a direct hit on the hole. Okay? They're not, pouring out or anything. They just have to hit the hole to get out. And the rate at which that happens depends on the speed. The faster they're moving, the more frequently one hits the hole right on. Okay, so what kinds of stuff should we be able to do with this? something like this. If it takes 1.25 minutes for 0.010 moles of helium to effuse, how long will it take for the same amount of ethane to effuse? These are make-you-think problems. Well, we just saw that the rate of A over the rate of B was equal to the square root of the molar mass of B over the molar mass of A. Do we know the molar masses of helium and ethane? Yeah, we can figure them out. So helium is going to be 4.003. That would be grams per mole. Since we're doing a ratio here, would it affect anything if we used grams per mole instead of kilograms per mole? No, it wouldn't, because the kilos are going to cancel out too. So we can just go ahead and use grams per mole here. What about ethane? 2 carbons times 12.01 plus 6 hydrogens times 1.008 equals 30. So this guy's a molar mass of 30.068 grams per mole. So let's call, which one do we want on the bottom? I'm going to call helium A, and ethane is going to be B. So the rate, I guess I really didn't need to do that, the rate of helium to the rate of ethane is going to equal the molar mass of ethane on top, 30.068, the molar mass of helium on the bottom, and the square root of that divided by 4.003 equals square root 2.741. What does 2.741 tell us? It tells us that the rate of helium effusing is 2.741 times as fast as the rate of ethane. Does that make sense? So we're given 1.25 minutes for 0.1 moles of helium. Well, rate. What units is rate? It's something per time, right? Something per unit time. So in this case, it's perhaps 0.100 moles per 1.25 minutes. That would be the rate for helium to effuse. They're asking us about the amount of time, how long, for the same amount. We're not really interested in the actual rate, we're interested in how much time. So if it takes helium 1.25 minutes for this much to effuse, is it going to take ethane more time or less time? It's going to take more time, right? Because the helium's faster. By what factor will the time be greater? 2.741. So we can take the 1.25 minutes and multiply it by 2.741, and that will give us the amount of time. .43 minutes. That's not a plug things into an equation and be done with it question. That's a, you got to think about it question. Any questions about the question? Is it break time? Maybe.